So today we will talk about the third segment. So we have discussed a little bit about discrimination. We have discussed a little bit about biases, and now we will talk about different ways to define fairness. So the first definition that is of our interests is called equalized odds. Okay. So equalized odds states that a predictor let's call it y hat satisfies equalized odds with respect to the protected attribute say Z and outcome Y if Y hat and Z are independent conditional on Y. In other words, you can write it as follows, which makes the definition much more mathematically succinct. P y hat equals 1 Z equals 0, Y equals Y should be equal to P y hat equals 1, Z equals 1, Y equals Y, where Y belongs to 0, 1, and Z equals 0 is the class which is not protected, and Z equals 1 is the protected class. Now, let us dig deep. What does this definition tell you?
The prediction is fair.
No, like prediction is fair. I mean, what does that mean? I mean, be more succinct in terms of like all the evaluation measures that you have learned in your machine learning 101 course. What is this definition telling? Irrespective of Z being 0 or 1 and Y taking up the value either 0 or 1, okay, the probability of Y hat is equal to 1. Okay, let me simplify this a little bit. You should start seeing these things even without simplification. Let's say, let me fix y to 1. What does this mean?
Probability remains same irrespective of whatever value
What
z
is this
takes.
probability? What is this probability? What is this probability? This has a name. You know this name very well. All of you, I'm sure.
Conditional probability
Conditional probability of what? Somebody said the correct answer.
of event.
The positive, what positive? This one is true positive rate. And if I have the other side, this is the so equalized odds. This is the easiest way to remember. Equalized odds constraints that the true positive constraints that the positive rates, both true and false, should be same for both the protected and the unprotected classes. Okay. So this is what is the constraint that equalized odds places, okay, on the predictor. So if you have a model which has to adhere to equalized odds, then the model has to keep its positive rates, that is both false positive and true positive rates, similar for the protected as well as the unprotected class. So I mean for similar across the protected and the unprotected class. Okay, so exact similarity is not always possible. So what people want to do is to have them as close as possible, okay, within some predefined threshold, which is very small usually. Okay.
So this should hold for all the attributes that we consider, right? Might be gender, skin.
Yes. So basically here we are assuming a single attribute, but this generalizes for all the sensitive attributes. Okay. The next definition is equal opportunity. So here a binary classifier is said to satisfy equal opportunity with respect to the sensitive attribute Z if what does this say? You should be able to see this. Huh? This is very similar to the previous definition. This is equal true positive rates across the two classes. So that means equal opportunity is a subset of the equalized odd. Okay, so this is one part of the condition is mandatory here. For equal opportunity, one part of the condition from equalized odd is mandatory here. Definition 3. Demographic parity. Also sometimes called the statistical parity. Okay, so a predictor y hat satisfies statistical parity if what does this mean? So whenever you see these kind of things, this should ring a bell, right? These are likelihoods. So what is it telling? That the likelihood of an outcome should be same across the protected and the unprotected class. Okay, so that is demographic or statistical parity. Then fairness through awareness. This is kind of a recursive notion. So we say that an algorithm is fair if it gives similar predictions to similarly situated individuals. Okay, so this is what is called fairness through awareness. We also have a converse of this, which is termed as fairness through unawareness. So an algorithm in this particular scenario is considered to be fair as long as any of the protected class attributes are not explicitly used in the feature set. Okay. Then there is which is called treatment equality. So treatment equality mandates that the ratio of the false negatives and false positives is the same for both protected and unprotected classes. Okay. So these are some of the very well-known definitions. There are quite a few others, but these are some of them, some of the ones that you actually come across every now and then. Okay, so that's why these are important to get acquainted to. and many of like our future studies that we will see will be dependent on one or many of these, one or multiple of these fairness constraints. Okay. Now, the fairness definitions that you have seen above can be categorized into three broad types again. These are called individual fairness, group fairness, and subgroup fairness. Okay. So what is individual fairness? So it should give similar predictions for similar individuals. What is group fairness? Treat different groups equally. In this case, you can assume that two different groups, protected and unprotected. Okay. And then there is this third one, which is the subgroup fairness. Which says that the desire here is to get the best of both ends. And typically, how do you achieve this? You first pick up some group fairness constraint. And then you say, for instance, something like equalizing FPR or FNR. Okay, you take up such group fairness constraints and then you test whether these constraints hold over a large collection of small subgroups. So here, as if these small subgroups are kind of your correlates of or analogous of individuals. Okay, and you are testing a group fairness constraint to be valid or not within each of these small subgroups. So that's how the subgroup fairness is achieved. Now, I will write down some of the definitions that we have learned just now, and you will tell me like in which class it belongs. So where do you classify demographic parity? Group or individual? Hello? No thoughts? Are people there in the class?
Yes, sir.
Or am I the only person? I'm getting a bit panicky. So what do you think demographic parity should be? In which class? Group or individual? I mean, make a guess. There is no harm in making a guess. Any one of you, make a guess. What is your best guess telling you? Huh?
Group, sir.
Group. Okay. Equalized odds?
Groups.
Groups. Equal opportunity? Of course, groups, because it is a subset. Fairness through awareness?
Individual.
Individual.
Yes, and fairness through unawareness is also individual. So I ran you through this exercise so that it becomes easy for you to remember. Now recall, like, the connect yourselves with the two case studies that we were doing. So in the ProPublica case study, what were we typically studying or trying to establish? Group unfairness or individual unfairness?
Individual.
ProPublica. Group or individual? Think carefully and tell. Why is it individual? One of you pointed out it's individual. Why do you think it is individual?
There we are just trying to predict the recidivism, sir, for a particular individual.
Recidivism for? We were
For a,
trying to find out false positive rates, false negative rates over an individual. Was it over an individual?
no, sir.
Over a group. So there, the group was dominantly two ethnic groups, right? Black and white. So this was an example of group unfairness. Okay, and therefore all the fairness constraints that are classified under group can be applied here. Now come to the next one, gender shades. What about this one?
This is also group, sir.
Group. Okay. So everybody agrees? Group? Group is the best way to classify? Everyone agrees that group is the best way to classify?
Yes, sir.
Acha. Now let me ask you, if you are agreeing, why not subgroup? Or could it be possibly subgroup? So if you think carefully, we were considering intersectional groups, which were black males, black females, white males, white females, right? And this adheres better to group or better to subgroup? This is a finer subdivision, right? So while black and white are like groups, here you have 4 different subgroups. So as if the black is getting further broken and the white is getting further broken into male and female, and here also male and female. Okay, so this is the notion of subgroup fairness. Basically, you break it into finer subdivisions and then you study the fairness or unfairness issues within each of the finer subdivisions. Make sense?
Yes, sir.
Okay. So you should be careful about nominating something as group or individual or subgroup. Okay. So now, once we have finished defining these 3 sets, so we have discrimination, we have bias, and we have fairness. And we have learned a lot of new jargons here. So initially it would be a bit like confounding, but I think like if you make a table of your own, things becomes much easier to remember. Okay, now we will come to the design of, based on all these notions that we have discussed so far, we will come to the notion of design of fair ML algorithms. Now, in order to do this design, what you basically do is a sort of an intervention. Okay, typically called a fairness intervention. Now, what is a fairness intervention? So you impose some fairness constraint at some chosen stage of the algorithm, of the ML algorithm. Okay, so if we broadly define the stages of any ML algorithm to input, processing, and output, then you can make interventions at all these stages. So let me call fairness intervention as FI for short. So you can have a fairness intervention at the input stage. You can have a fairness intervention at the processing stage. You can have a fairness intervention in the output stage. So what does this mean? So here, basically, you do pre-processing on the data set. So that your results are fair. For instance, say you discard all the sensitive attributes from your feature set. This could be a simple pre-processing. Okay, so this is an input stage intervention. Then the processing stage. This is actually an interesting stage, and most of the fairness intervention literature actually talks about this particular stage. So what do you do here? Here there are two ways to handle this. Okay. Now, if you recall that any ML algorithm is built on some objective function. Okay. Now, if you are doing an in-processing fairness intervention, it's called in-processing fairness intervention, then what you try to do here is either you change the objective function to satisfy the fairness criteria, or you impose a constraint when you solve for the objective, so that the fairness criteria is satisfied. And we will look into this particular type in details. Okay, so we will take up one specific use case where we will see end to end how you can impose constraints on the well-known objective functions, okay, in order to satisfy some fairness criteria. Okay, and then there is the post-processing. So here, what you do, once your results are already in place, you try to use some sort of a wrapper on the output. Okay, this could be a heuristic, a vanilla heuristic, in order to obtain fairer results. Okay, so these are the three stages in which you can intervene a machine learning algorithm in order to have it obey or satisfy one or more fairness criteria. Okay, so now, as I had already told you, that the fairness criteria can be imposed on classification algorithms, regression algorithms, as well as embedding generation algorithms. And we will specifically take up these two and look into how fairness criteria could be introduced in these algorithms. So the first among this is the one by Zafar et al, where so there had been quite a few other studies also around this, but this paper by Zafar and Krishna Gumadi, this is one of the like cornerstone papers in this area, and the entire formulation is extremely neat, and therefore we are going to look into this particular algorithm. Okay, the way they introduced fairness. So here, as per the authors, they had two things in mind. So they wanted to have two criteria, and that's how actually adhere to fairness. One was avoid disparate treatment, and the other was avoid disparate impact. Okay, so these were the two things that the authors wanted to avoid in a standard machine learning classifier, and that's how they wanted to impose fairness criteria. Now, for disparate treatment, they went with a very vanilla definition. Of course, you can have a more complex formulation of the disparate treatment, but for the authors, they took a very vanilla measure, and what they said is that sensitive attributes cannot be used for decision making. Okay, so basically, if this is the feature set, then this should be disjoint from the sensitive attribute. And you can have n number of such sensitive attributes. Okay, so this should be the feature set should not include the sensitive attribute. Okay, when a decision is made, the feature set should not include the sensitive attribute. That was their simple definition of disparate treatment. What they were more interested in was to avoid disparate impact. Okay, and in order to avoid disparate impact, they resorted to a well-known rule in the literature called the P% rule. Okay, so what is the P% rule? The P% rule states that the ratio of the percentage of users with a sensitive attribute having to the percentage of users without the sensitive attribute having should be no less than P is to 100. Okay, now you must have a question that what is this ugly looking thing, right? So basically what it is telling that the ratio of the percentage of users having a sensitive attribute and or possessing a sensitive attribute and having d theta x greater than 0 to the percentage of users without the sensitive attribute having d theta x greater than 0 should be no less than p is to 100. Can anyone guess what is d theta x? Any guesses? What is d theta x? Come on. At least guess something. Wild guess. D theta x is the signed distance of the feature vector x from, at least fill this part, from where? This is a classification algorithm.
Decision boundary.
Very good. From the decision boundary. Decision boundary that your classifier learns. Okay, we will stop here and tomorrow we will discuss the rest of the stuff. We will like formulate the definition of the decision boundary, its equations, and then we will see like how the authors achieve disparate impact. And if time permits, we will also look into the results. Otherwise, we will look into the results next week. So any questions up to this point?
So, sir, in order to say a model is fair, we have to verify all these equalized odds or equal demographic opportunity. Those things we should check, right? Or it is not the exhaustive list.
No, it's not an exhaustive list. And also like, these fairness constraints, these are very application specific. You choose certain things in certain places.
Okay.
Any other
I
questions?
just had one more question, sir. So
Yes, sure.
in case of equal opportunity definition, I think the definition was from the binary classifier. But in case of gender sets, I think we had 4 intersectional groups, right?
Yes.
So yeah, I think that should also holds there also, right? That equal opportunity thing.
Yes, it will hold. So it is generalized. So the binary classifier is kind of a first step to understanding it. But
Yes.
these definitions hold on all multi-class classifiers, first of all, and second of all, it holds on multiple Zs. So
Yeah,
you can have many
multiple attributes, you mean?
Yeah,
Right?
you can have many sensitive attributes. So these definitions are easily generalizable to those differences, to those varieties. But for ease of understanding, we typically like restrict ourselves to the binary state. Also, as you will see here, like when I will like design the fair classifier, we will assume that we have only one Z, which is 0 and 1. But it can be easily generalized. Any other questions?
No, sir. Thank you.
Okay. So we will stop here and see you tomorrow.